Welcome to the deep dive. Today, we're jumping straight into the world of abstract algebra, exploring some really um, fundamental ideas, ideals, factorings, and homomorphisms.
That's right. And you, our listeners, many of you are in master's programs for math education, teaching high school math. Well, you might not be directly teaching these specific concepts, but we think you'll discover some surprisingly valuable connections.
Yeah, connections back to the math you're already familiar with, hopefully.
Exactly.
Absolutely. So we'll be using chapters 14 and 15 of Gallien's Contemporary Abstract Algebra as our roadmap, basically.
Good source.
Yeah. Our goal in this deep dive is really to pull out the most important insights, the nuggets from these chapters, explain them clearly, and maybe, just maybe, create a few of those aha moments.
Where the abstract stuff clicks with what you see every day.
Right, where those abstract structures connect to familiar high school topics. Let's get started.
Okay, let's begin with ideals. Chapter 14 kicks off by defining what an ideal A of a ring R is. Essentially, a subring A of R is an ideal. Specifically a two-sided ideal. If for every element R in the bigger ring are in every element A in the ideal A, both R times A and times R are also elements back inside A.
Okay, hold on. Let's unpack that a little. So first off, it's got to be a subring.
Yes, first requirement.
Which means it's a little ring living inside the bigger one, R.
Right, closed under addition, subtraction, and multiplication.
Okay. But then this ideal thing has this extra property.
Yeah.
You call it absorption.
Exactly. It kind of absorbs elements from the larger ring when you multiply.
So anything from R times anything from A, the result gets pulled into A.
Pull back into A, yes.
Okay.
Both ways. R times A and A times R. It's like A has this gravitational pull for multiplication by elements from R.
Okay. That's a helpful image.
And, there's a really useful shortcut for checking if something's an ideal. It's theorem 14.1, the ideal test.
Ah, good. Saves checking all the subring stuff first.
Well, almost. It bundles some of it. It says a non-empty subset A of a ring R is an ideal if, and only if, two conditions hold.
Okay, what are they?
First, if you take any two elements A and B that are in A, their difference, A minus B, must also be in A.
Right, that sounds like the subgroup criterion for addition, closure under subtraction.
Yep, it ensures it's an additive subgroup. And second, for any element A in A and any element R from the whole ring R.
This is the absorption part.
This is the absorption part. Both R times A and A times R must be in A.
Got it. So closure under subtraction within A and this two-sided absorption of multiplication from R into A. That test seems much more direct.
It really is. It captures the essence.
So what are some examples, like concrete examples of ideals?
Gallian gives several good ones.
Yep.
First, in any ring R, the set containing just the zero element,
The trivial one?
The trivial ideal, yes.
Yeah.
That's always an ideal. I mean, 0 minus 0 is 0. That's in there. And anything times 0 is 0, which is also in there. So check and check.
Makes sense.
And also, the entire ring R itself is always an ideal of R.
Right, because R is closed under its own operations, and multiplying an element of R by another element of R obviously stays in R.
Precisely. Those are the maybe less interesting examples in some ways.
Okay, give us a more interesting one.
All right. Think about the ring of integers, Z.
Okay.
For any positive integer n, the set of all multiples of n, we write it as nz. I got 2n, and then there's n is 2n.
Like 5z would be 1 of 10, and a 5, 0, 5, 10.
Exactly. That set, nz, is always an ideal of z.
Okay, let's try the ideal test on that. Take two multiples of n, say n and bn.
Right.
Their difference is n minus bn, which is ab times n. That's definitely a multiple of n, so it's nnz.
Yep.
First condition met.
Good.
Now, take any integer r, just any old integer, and multiply it by an element from nz, say n. So r times n. That's arrow times n. That's also a multiple of n, so it's back in nz.
And the other way, n times r.
Well, integers commute, so on times r is the same as r times on, which we just showed is in nz. So yeah, it works. nz is an ideal.
Perfect. Now let's add a little complexity. If we have a commutative ring, R with unity meaning it has a multiplicative identity, like 1 in the integers.
Okay, commutative, like the integers are real numbers.
And then for any element A in R, the set of all multiples of A by elements of R, so the set A, ray R, is in R, that forms an ideal.
Ah, and this is called a principal ideal, generated by just A.
That's the one. The principal ideal generated by A. Notice we needed commutativity here.
Why? Oh, right, because you defined it as ray R in R.
Yeah.
If it wasn't commutative, we'd also have to worry about whether R is in that set too, for it to be a two-sided ideal.
Exactly. So in a commutative ring with unity, this construction works smoothly. And in the integers, they're ideal n, z we just talked about, is the principal ideal generated by n.
Because any multiple of n is just some integer r times n.
Right.
Yeah. Okay. What about polynomial rings? They always feel a bit more abstract.
Let's take R bracket x, the ring of polynomials with real coefficients.
Okay, math dig.
Consider the set A of all polynomials fx in R bracket x such that f0 goes 0.
So polynomials with no constant term, like 2x or by 2, 3x.
Exactly. Is this an ideal? Let's check. Take two polynomials fx and gx, both with f0 0, 0, 0, 0, 0. What about fx gx?
Well, the constant term of f, 0. The constant term of g is 0. So the constant term of the difference is 0 minus 0, which is 0. So yes, the difference is in a.
Good. Now take fx in a, so f0, and multiply it by any polynomial hx from R bracket x. What about the product, hsx, with its constant term?
The constant term of the product comes from multiplying the constant terms of hx and fx. Since fx's constant term is 0, the product's constant term must be 0.
Right, so hsx is back in a, and since R bracket x is commutative, fxx is the same. So yes, a is an ideal.
That's a neat example. It connects the ideal structure to a property of the functions evaluating to 0 at a specific point.
Here's another one, this time in z bracket x polynomials with integer coefficients.
Okay, math BBZ.
Let I be the set of all polynomials in z bracket x where all the coefficients are even.
Like 2 by 2 plus 4 or 6 by 8.
Yep. If you subtract two such polynomials, say px and qx,
then each coefficient in px, qx will be an even integer minus an even integer, which is still even. So the difference is in I.
Okay, now multiply px, all even coefficients, by any polynomial hx from z bracket x, which might have odd coefficients. What about the coefficients of px, hx?
Let's think. Each coefficient in the product is formed by sums of products of coefficients from p and h. Since every coefficient in p is even, every term in those sums will have an even factor from p, so the sum of those terms must be even.
Right.
All coefficients of the product will be even, it stays in I.
Exactly. So I is an ideal of z bracket x. The evenness is absorbed, you could say.
Cool.
And we can generate ideals from more than one element too. Like in z bracket x, the ideal x is just all polynomials with x as a factor, so no constant term. We saw that was an ideal.
Right.
But we could also look at the ideal generated by two things, say 2x.
Generated by the constant polynomial 2 and the polynomial x. What's in that?
It turns out to be all polynomials in z bracket x whose constant term is even.
Let me think. Any combination looks like px times 2 plus qx times x. The qx times x part has no constant term. The px times 2 part has an even constant term, twice the constant term of px. So yeah, adding them gives a polynomial with an even constant term. Makes sense.
You got it. So ideals are these special subrings with the absorption property.
Okay, I think I'm getting a better handle on them now. So
yeah.
What do we do with ideals? Why are they important?
Great question. This leads us straight into factor rings, also in Chapter 14. Once you have a ring R and an ideal A inside it, you can use A2. Oh, well, essentially divide R by A to create a new ring.
Divide a ring. How does that work?
It's very much like the idea of factor groups in group theory, if you've seen those. You use the ideal A to partition the ring R into pieces.
Pieces. You mean like cousets?
Exactly. The factor ring, which we write as R slash A or R mod A, its elements are the cos of A and R. Remember what a coset is. You take an element R from R, and you add the entire ideal A to it.
So R plus A, R plus A, where A is any element in the ideal A. It's like shifting the whole ideal A by R.
That's a perfect way to picture it. The factor ring RA is the collection of all these shifted sets, these cosets, as R runs through all elements of R.
Okay, so we have the elements of this new thing, RA, they're sets, these cosets. But how do we make it a ring? We need addition and multiplication for these sets.
Right, and the definitions are pretty natural, actually. They mimic the operations in the original ring R. If you have two cosets, say R plus A and S plus A, their sum is defined as R plus A plus S plus A, R plus S plus A.
So you just add the representatives, R and S, and take the coset of the result.
Exactly. And multiplication is similar. R plus A times S plus A or S plus A. You multiply the representatives R and S and take the coset of that product.
Okay, that looks simple enough. But wait, what if I chose a different representative for the same cos? Like if R plus A is the same set as R plus A, would using R instead of R give me the same answer when I add or multiply? This sounds like that well-defined issue.
You've hit the crucial point. And this is where ideals are absolutely essential. Theorem 14.2 addresses this directly. It says, let R be a ring and A be a subring. The set of cosets RA forms a ring under these operations if and only if A is an ideal of R.
Whoa. So that absorption property of ideals is exactly what guarantees that the multiplication of cosets makes sense, no matter which representative you pick.
Precisely. Without A being an ideal, the multiplication, R plus A, S plus A, and R's plus A might give you different results depending on your choice of R and S for the same cosets.
Yeah.
The ideal property fixes that. It makes the operations well-defined.
That's actually pretty profound. The definition of an ideal is tailor-made to allow this factor ring construction.
It really is.
Yeah.
Now let's look at some examples. The absolute classic is Z mod NZ.
Math B Z. Okay, R is the integers, math B B Z is the ideal math B B Z.
And what is this factor ring math? It's exactly now the interest modulo n that we all know and love.
No way. Really? How does that work?
Think about math BBZ. The elements are 0, 1, 2, 3. What are the cosets of 4 math BZ?
Well, there's 0 plus 4 math BZ, which is all multiples of 4. Then 1 plus 4 math BZ, which are integers like 1 of 7 math B3, 1, 5, 9. All the ones with remainder 1 when divided by 4.
Keep going.
Then 2 plus 4 math BTZ and 3 plus 4 math BZ, remainder 3. And if I try 4 plus 4 math BZ, I just get back to 0 plus 4 math B. So there are exactly 4 distinct cosets.
Right, and they correspond perfectly to the elements 0, 1, 2, 3 in math BZ. Now check the operations. How do we add cosets? Say 2 plus 4 math plus 3 plus 4 math BZ.
According to the rule, it's 2 plus 3 plus 4 math BZ, which
Yeah.
is 5 plus 4 math BD.
And which coset is 5 plus 4 math BZ the same as?
Since 5 has a remainder of 1 when divided by 4, it's the same as 1 plus 4 math B4.
And what's 2 plus 3 in math BBZ?
It's 5, which is 1 mod 4. It matches.
See. And multiplication. 2 plus 4 math BB times 3 plus 4 math BBZ.
Yeah.
Would be 2, 3 plus 4 math BBZ plus 4 math BBZ. Since 6 is remainder 2, this is the same coset as 2 plus 4 math BBZ.
And in math BBZ 4, 2 times 3 is 6, which is 2 mod 4.
It works perfectly. So modular arithmetic, the stuff we teach with clocks and remainders, is actually happening inside a factor ring of the integers.
That's exactly right. It gives a much deeper structural understanding of why modular arithmetic works the way it does. It's not just arbitrary rules, it's the structure of a factor ring.
That's a fantastic connection for teachers. Okay, what was that other wild example you mentioned? Something about complex numbers.
Yes. Consider R bracket x, polynomials with real coefficients, again, and let I be the principal ideal generated by the polynomial by 2 plus 1. So I by 2 plus 1.
Okay, all multiples of by 2 plus 1. Now, look at the factor ring R bracket x mod I. So, math wrangle by 2 plus 1 wrangle. It turns out this factor ring is isomorphic to the complex numbers.
Whoa, hold on. How?
Yeah.
The elements of the factor ring are cosets of polynomials.
Right. They look like fx plus I. But what does it mean to be mod I? It means anything in I is equivalent to 0 in this new ring.
Okay.
Well, by 2 plus 1 is definitely in the ideal I equals by 2 plus 1.
Sure, it's 1 times itself.
So in the factoring that by 2 plus 1 wrangle, the coset by 2 plus 1 plus I is the 0 coset, 0 plus I. This means, effectively, by 2 plus 1 plus 0p this ring.
Which means by 2 equals 1.
Exactly. In this factor ring, the coset, represented by x, behaves like a number whose square is -1.
Like I.
Precisely like I. Now think about any polynomial fx. Using polynomial long division, you can divide fx by 2 plus 1 and get a remainder. Say x plus b, where a and b are real numbers.
Right. Fx by 2 plus 1 plus x plus b.
So in the factor ring, fx plus I is the same coset as qx do plus 1 plus x plus b plus I. But qx plus 2 plus 1 is in the ideal I, so it's equivalent to 0 here.
So fx plus I is the same coset as just x plus b plus I.
Yes. Every coset can be uniquely represented by a linear polynomial x plus b plus the ideal I.
And if we identify the coset x plus b plus I with the complex number b plus a, wait, should it be a plus by?
Let's be careful. If we identify the coset x plus I with I, then the coset x plus b plus I corresponds naturally to b plus a. Or maybe more standardly, let's think of the coset as a plus bx plus I. If x acts like I, this looks like a plus by.
Okay, let's go with that. The coset a plus bx plus I corresponds to the complex number a plus by.
Now, how do operations work? A plus bx plus I plus c plus dx plus I, a plus c plus b plus di.
Okay, addition works. What about multiplication?
A plus bx plus I, c plus dx plus I, ac plus add plus bcx plus bdx plus I. But remember, in this ring, x2 is equivalent to -1.
Right, so that bdx2 becomes dibbbd.
Exactly. So the product is acbd plus add plus bcx plus I.
Which corresponds exactly to a plus by, c plus di, acbd plus add plus bci. It's the same.
It's precisely the same structure. The factoring mathedbx wrangle by 2 plus 1 wrangle is algebraically the complex numbers by BCI.
That is genuinely amazing. It shows that IWB1 isn't just some rule we made up. It emerges naturally from polynomial algebra when we quotient by the right ideal.
Wow, it's a beautiful connection. And think about teaching complex numbers, maybe not showing the full factoring construction, but
Yeah.
hinting that I comes from solving by 2 plus 1, 0 ways within a larger system could be really powerful.
Absolutely. Okay, so we can also have things like math BBZ, Langle by 2 plus 1 Wrangle,
Yeah.
right, where coefficients are integers.
Yes, and that gives you the Gaussian integers, often written math BBCI. Elements look like a plus by, where A and B are integers. It's a ring, but not a field like math BBC. For example, 2 doesn't have a multiplicative inverse in math BBCI.
Got it. Now, the chapter also mentions prime and maximal ideals briefly. What's the gist there?
Right. They connect the properties of an ideal A to the properties of the factor ring Ra. A prime ideal A in a commutative ring R is a proper ideal, not R itself, with a property similar to prime numbers.
How so?
If a product, A times B, lands in the prime ideal A, then at least one of the factors, either A or B or both, must already be an A.
Ah, okay. Like if a prime P divides A, then P must divide A, or P must divide B. That makes sense.
Exactly the analogy. And a maximal ideal A is a proper ideal, such that there's no other ideal B strictly between A and the whole ring R.
Meaning if B is an ideal and A is inside B and B is inside R, then either B has to be A or B has to be R. There's no room between A and R.
That's it. It's maximal because you can't make it any bigger without it becoming the entire ring.
Okay, prime relates to products, maximal relates to size or containment. Why are they important for factor rings?
Because they tell you exactly what kind of ring Ra is. Theorem 14.5 says, in a commutative ring R with unity, Ra is an integral domain.
An integral domain,
Yeah.
commutative ring with unity and no zero divisors, right?
Right. Ra is an integral domain if and only if A is a prime ideal.
Wow.
And Theorem 14.6 says Ra is a field.
Where every non-zero element has a multiplicative inverse.
If and only if A is a maximal ideal.
So the type of ideal directly dictates the structure of the factor ring. That's incredibly powerful.
It really is. For example, we know math BBZ, which is D math BZ, is a field when P is prime.
Right.
So Theorem 14.6 tells us that the ideal PBZ must be a maximal ideal in math BZ.
And since fields are also integral domains, math BBZ is an integral domain, so mutable BBZ must also be a prime ideal in math.
Exactly. And in commutative rings with unity, it's always true that maximal ideals are also prime ideals.
This ties things together really nicely. Okay, let's shift gears to chapter 15, ring homomorphisms.
All right. Homomorphisms are all about structure-preserving maps between algebraic structures. A ring homomorphism is a map, let's call it phi, from a ring R to a ring S.
Okay, 5,
That preserves both ring operations, addition and multiplication. Meaning two things must hold for all elements A and B in R. First, phi of A plus B must equal phi of A plus phi of B. It preserves addition.
Phi A plus B plus phi B.
Got it.
And second, phi of A times B must equal phi of A times phi of B. It preserves multiplication.
Phi of B. Okay.
Yeah.
So it respects both operations. It's like doing the operation first in R, and then mapping is the same as mapping first to S, and then doing the operation there.
That's a perfect way to put it. It doesn't matter if you operate then map or map then operate.
And if this map phi is also a bijection 1-to-1 and onto.
Then it's called a ring isomorphism. And we say the rings R and S are isomorphic. Written R is congruent to S symbol.
Isomorphic means they're essentially the same ring structurally.
Yeah.
Just maybe wearing different clothes, different labels for elements.
Exactly. Algebraically identical. We saw an example earlier, Nath math by 2 plus 1, Wrangle Kong math by 2.
Right. What are some other examples of homomorphisms? Our really fundamental one is the mod-n map. Let phi go from the integer z to z sub n, defined by phi, a mod n by phi 1.
We know from properties of modular arithmetic that a plus b mod n is a mod n plus b mod n, and ab mod n is a mod n b mod n, mod n. This map phi perfectly preserves the operations. It's a ring homomorphism.
Makes sense. It feels very natural connecting math B to z.
Another one, polynomial evaluation. Pick a specific real number c. Define a map phi from R bracket x to R.
A math method fx, fc. Just plug in c.
So evaluating a polynomial at a fixed point c.
Yep. Is it a homomorphism? Well, f plus gc is fc plus gc. So phi f plus g plus phi.
Preserves addition.
And fgc is fc times gc.
Okay, listen.
So phi's multiplication, yes, it's a ring homomorphism.
One more, complex conjugation. Map phi from c to c. Phi a plus bi is ab.
Switching the sign of the imaginary part, we know the conjugate of a sum is the sum of the conjugates. And the conjugate of a product is the product of the conjugates. So it preserves both operations.
Right.
And it's one-to-one and onto. So complex conjugation is actually a ring isomorphism from math BBC to itself.
Interesting. An automorphism. Okay, so homomorphisms preserve structure. Chapter 15 also talks about the kernel of a homomorphism. What's that?
The kernel of a ring homomorphism day, R, right arrow S, written ker, is the set of all elements in the starting ring R that get mapped to the zero element of the target ring S.
So ker in R where 0s is the additive identity in S.
Exactly. It's everything in R that gets killed or annihilated by phi, sent to zero.
This sounds just like the kernel in group theory stuff that goes to the identity.
It's the direct analog for rings. And just like in group theory, where the kernel is a normal subgroup, here the kernel has a special structure too, Theorem 15.2 says. The kernel of a ring homomorphism is always an ideal of the domain ring R.
An ideal. There is again. So the set of things mapping to 0 automatically satisfies those ideal properties, closure under subtraction and absorbing multiplication.
That's right. It's quite remarkable.
It really shows how central ideals are.
And this leads directly to maybe the most important theorem connecting all these ideas, the first isomorphism theorem for rings, Theorem 15.3.
Okay. Sounds big. What does it say?
It says if you have a ring homomorphism, arapical, then the factor ring you get by modding out R by its kernel. That's R ker P.
Right. Take the ring R, divide by the ideal ker.
The factor ring is isomorphic to the image of phi, denoted tearaway.
The image being just the set of all outputs in S, all the things that actually get hit by phi.
Exactly. It's a subring of S. So the theorem states R ker high.
Wow. Okay. So taking the domain ring, quotienting by the stuff that maps to 0, gives you something structurally identical to the set of actual outputs of the map.
Precisely. It fundamentally connects factor rings, kernels, which are ideals, and the image of a homomorphism. It tells you that the image's structure is captured by this factor ring construction.
Can we see this with our examples? Like the mod n map.
Sure. Right arrow, math b min by fort min and what's the kernel?
Kerfine is all integers as such that a mod n equals 0. That's just all the multiples of n. So kerfine n is n.
And what's the image? What outputs do we get in
Grab all of them, right? 0, 1, 2, n 1. So the image is all of math b bean.
Yep. So the first isomorphism theorem says math b bin, math b b, n b n n.
Yep.
So the first isomorphism theorem says math b z, plugging in what we found. How about the evaluation map? Math b's imicant, what is f phi? Where the Fanthanoid map is right arrow by math x.
Okay, the kernel, kerfine, is all polynomials fx such that fc0.
And what do we know about polynomials that have c as a root?
The factor theorem. They must have xc as a factor. So the kernel is all multiples of xc. That's the principal ideal generated by xc.
Cursor x is c.
Excellent. And what's the image? What real numbers can we get as output xc?
Well, if I just take the constant polynomial fxr, where r is any real number, then fc is just r. So I can get any real number as output. The image is all of math br.
Perfect. So the first isomorphism theorem says math br, plugging in math bic, wrangle Kong.
Another beautiful result. Quotienting the polynomials by the ideal of polynomials vanishing at c gives you back the real numbers. It's like forcing x to be c.
That's a great intuition. And just to complete the circle, Theorem 15.4 says that every ideal A of a ring R arises as the kernel of some homomorphism, specifically the natural or canonical homomorphism force. R, right arrow, RA defined simply by R plus A har.
Just mapping an element to its own coset.
Yes. That map perhaps is a ring homomorphism, and its kernel is exactly the ideal A you started with. So ideals are kernels, and kernels are ideals. There's this perfect correspondence.
It's a very deep duality. One last thing from chapter 15 is a brief mention of the field of quotients, Theorem 15.6.
Okay.
It's basically the formal process for building the rational numbers $math BDQ from the integers $BBG. It shows that you start with any integral domain D, where multiplication works nicely, no zero divisors.
Like the integer.
You can always construct a field, call this field of quotients, that contains D, and where every non-zero element from D now has a multiplicative inverse. It's like formally creating fractions AB, where A and B are from D, and B isn't zero.
Ah, so it guarantees we can always embed an integral domain into a field where division by non-zero elements is always possible, just like math BBZ sits inside math BBQ.
Exactly. It's the algebraic justification for constructing rationals from integers.
Okay, this has been a fantastic tour through ideals, factor rings, and homomorphisms. Now let's really bring it home for our listeners. How do these abstract concepts connect back to or inform high school math teaching?
Well, we've hit on some key ones already. The most obvious is math BBZ, modular arithmetic. Understanding it as math BBZ gives it a solid structural foundation.
Right, it's not just quark arithmetic, it's a factor ring. And the idea of ideals in math BZ being math BZ, all the multiples, that directly relates to divisibility, factors, multiples, core number sense topics in high school.
Absolutely. Even thinking about things like the set of even integers, $2 math BZ, as an ideal might offer a different perspective.
And what about homomorphisms, that structure-preserving idea?
It's maybe more subtle there, but think about function transformations in algebra class. When you shift a graph like y of x to y of xve or scale it y of eh, you're applying a map that changes the function but preserves certain underlying relationships or shapes.
Okay. It's not a ring homomorphism, but it carries that flavor of mapping while preserving some structure.
Perhaps. It might just be a way to think about transformations more abstractly. But the big one, I think, is the connection we saw. Math BGC plus 1 Math BBC.
Yeah, that was mind-blowing. It gives real context to 20 color equals nations of Deller.
It shows it's not arbitrary. It's a consequence of wanting to solve by 2 plus 1 equals 0 within a consistent algebraic system built from polynomials. It provides a much richer why for complex numbers.
So the main takeaway for teachers isn't necessarily to teach ideals and factor rings directly.
Probably not in most high school curricula, no.
But understanding these concepts provides a deeper, more connected view of the mathematics they are teaching. It strengthens their own understanding of the foundations.
Precisely. It helps see the bigger picture, the unifying structures underneath seemingly different topics like modular arithmetic, divisibility, polynomials, and complex numbers. It can lead to richer explanations and finding connections you might not have noticed before.
So it's about building that deeper appreciation for the interconnectedness of math, which can then inform how we present topics, even if we don't use the abstract algebra terminology.
Exactly. And maybe it sparks some curiosity in students, too, if you can hint at these deeper structures.
Okay, so here's a final thought for everyone listening to mull over. We've talked about ideals absorbing multiplication and factor rings as quotients, dividing by an ideal. How might thinking in terms of ideals or quotients offer new ways to explain or understand concepts even back in elementary algebra?
That's provocative.
Yeah.
When we talk about equivalent fractions, 12, 24, 36, they all represent the same rational number. Is there a sense in which we're working with equivalence classes there, maybe analogous to cosets?
Or simplifying algebraic expressions. Maybe factoring out a common factor is related to identifying an ideal structure. It's definitely something to think about.
Yeah, how do these fundamental ways of organizing algebraic structures, identifying special subsets, ideals, and forming new structures by treating elements as equivalent quotients manifest themselves, perhaps implicitly in the math taught much earlier?
That's a great question to reflect on. Explore the curriculum you teach and see if you can spot shadows of these ideas. It might just change how you see things.
Definitely worth considering.
Well, thank you for this incredibly insightful deep dive today.
My pleasure. It was fun exploring these connections.
And thanks to all of you for listening. We hope this gives you some new perspectives to bring to your teaching.